This is the Amp Hour Podcast. Released June 23rd, 2019. Episode 448. An interview with Rintoul. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And I'm Jean from Mind's Eye Biomedical.
Welcome, Jean. How you doing?
I'm pretty good, yeah.
I'm excited to talk to you about the intersection of like bio and electronics. I think that is like, obviously it's a way of the future, but it's like, it's such an important field. You know, like anything in medical is obviously very important. How did you get into that? Or well, maybe a little bit first about like what Mind's Eye is meant for, and then we'll get back into it. What you got there, how you got there.
Yeah, sure. So Mind's Eye Biomedical is my product development consulting company. It also holds the Spectra open source electrical impedance tomography kit, which is a low cost way to do biomedical imaging. And I came to that. I've actually been in biosensor wearables for about over 10 years, maybe 12 or 13 years in startups in Silicon Valley. And I've made a few medical devices as part of that as well. And I sort of thought, there's some problems with getting, as you said, bioelectronics is really important, but it's really hard to actually get things through the regulatory process, which things should go through, but it stifles innovation. And I was thinking, you know what's a much faster and interesting route to market is to encourage innovation, because I think the truth of the matter is that it's actually not that hard to innovate in this area. I'm not saying it's super easy and you'll just like fall over and Bob's your uncle.
Right. It's not like a content area that's super easy. You're saying it's the area is vast. It's a plum for new ideas.
It is really plum, but all the people, like so many people, are really put off going anywhere near it.
Oh, I'm terrified personally. Like I don't even know where to start.
Yeah, and I think so basically you get all these electronic hackers. You've got the Raspberry Pi situation. You've got the Arduinos and the Maker movements. Although that's obviously having a little hiccup right now. But you have all these like wonderful open source movements, and they're just firing along, and they're teaching people. More people are learning how to, get involved with this sort of hardware, software knowledge base, and that's really awesome. But I haven't really seen the same thing for biomedical,
right.
And that's because it seems really threatening. And so I was thinking, is there a way to get into it in a really safe way? So you want to be safe. I'll just put that one out there. You also can't be diagnostic. Otherwise, or you can't mention anything diagnostic or say anything diagnostic, as that also means that you should have regulatory approval. But let's just say you wanted to do something like see inside the body.
Sure.
Now, yeah,
you
right?
got a tummy ache, and you're like, "What's going on here?"
Did I swallow some nails, or like, what? Yeah, right. So, and I think that's like seeing inside the body is actually a really good place to start. So if you can do that in a safe way and get information about what's inside that you can't see using your own eyes, that's really amazing information.
Right.
You could put it on your, measure your stomach changes, as you just mentioned, or other organ changes, heart changes, lung changes, and we can sort of go into the whole variety of other applications.
Sure.
Later, but
yeah, well, I was thinking too of like when I think about like looking inside the body, I think about X-rays and CT scans and like really big, expensive, and dangerous things, like you're saying. And so I guess I never even knew this was an option. Like, how do you make it so that it actually is available to people?
So that's kind of what inspired me. It's because So CAT scans use X-rays, and X-rays are really bad for you. They're actually the biggest source of radiation in the United States. So you
Oh,
really don't
really?
want to get a CAT. Yeah, you don't want to get a CAT scan. Don't get a CAT scan unless you know you really really
Right.
need one. You have to get
No
one.
casual Friday night cat scans, you're saying?
Yeah.
Yeah.
No. So don't just you can't really have one in your house. They're a little large. They cost a few $1 million. So it's sort of out of range of the kind of experimental or hacker community. They are cool though. And MRIs are even cooler. Like that is just such beautiful physics involved in an MRI.
Yeah.
But
Yep.
a few $1 million. You've got to have your own helium quenching chamber. You've got to have dedicated staff that are highly trained to manage it. It's currently 2/3 of the world, like the bottom, uh, the economically disadvantaged people, they don't have any access to any kind of medical imaging at all. So it was sort of like, well, there's these excellent sort of high end things that we have, and there's nothing
Right.
else.
And then the next one down
So
is like eyeballs and like
yeah,
maybe listening with your ears, I guess, is kind of looking inside with your ears, I guess, right? Or like a stethoscope, but that's barely it.
no, exactly. Well,
Yeah.
ultrasound is
Sure.
like the ear extension.
Well, yeah. So, past guest of the show, Greg Charvat he worked on the Butterfly. That's the portable one, but
Mm.
even that's still $2,000, right? That's still pretty expensive and based on smartphones and everything else. So
Yeah. And I don't believe it's open source.
that's true.
That's really sexy. I believe that is that the MEMS based ultrasound.
That's right. Yep. Yep.
I love that. And I think that's super awesome. And I want one. And I would love to be playing with a kit. I would love to make a kit with MEMS based ultrasound sensors, but to tell you the truth, I've actually had to look for them. I can't just buy
Oh yeah.
them. You can't readily buy those just yet because they're all super patented into these. There's a few different companies doing them and a few different labs that are sort of like working on them, and they're awesome. But I haven't been able to get my hands on one.
Yeah. I think that's probably the most secret of the sauce that they have. So I'm sure they're keeping that pretty close right now.
So there's huge potential there to unlock this area, as I said before. And what I did is look at there's a whole bunch of labs that are using current-based techniques, and why that's kind of cool is because you don't need any special equipment. You don't need a specially manufactured, wafer scale MEMS process to make your special ultrasound sensor here. You just need AC current. So you need alternating current. And that's it. And I'm using alternating current between about 100 hertz and 80 kilohertz to get different information about the body. And then it's actually using the same reconstruction technique that a CAT scan uses,
Oh wow.
which is an inverse radon transform to recreate an image. Now, the image itself isn't as high resolution as an MRI or a CAT scan, but nonetheless, I'm getting an image, and you can get an
Right.
image with AC current, which I think is actually kind of cool.
Can you walk us through the that's very cool. Can you walk us through like the physics of that, like how that works? I don't quite get that.
Well, yeah. So let's just think of the body as a circuit for a second, and I think that's the key is just imagining a single cell. And if you look at a cell, you can so you've got extracellular and intracellular fluid, and then you have the cell membrane. The cell membrane is kind of like a capacitive layer. And the different intracellular, extracellular fluids, they have different resistances. So you can kind of model a circuit right there. Now you have a whole bunch of these cells stuck together, and different cells from different parts of your body are going to have different values, different resistances and capacitances. So basically what that gives you is a different dielectric spectrum when you send different alternating currents through your body. So an example of that would be if you send a high frequency current through, it will go straight through cells, getting the intracellular fluid. If you send a lower frequency current through, say around 1 kilohertz, it will get the extracellular fluid instead. So using that information, you can differentiate different materials in different locations. And the basics of that, that's the basic methodology underneath. On top of that, you can apply all these mathematical algorithms, but the basic understanding is just that, the body is this network of resistors and capacitors. And we're just modeling that. And there's a few ways that you can solve for that. One of them is solving Maxwell's equations. But there's a few other techniques that we can go into as well. And the base tomographic technique is just so you send current in, and then you measure the voltage on the other electrode. So say you have a tank with 32 electrodes, and you send a signal in and you measure it on the other electrodes. It will be perturbed based on or impeded would be the correct term, because it's impedance tomography, based on what's in the way. So if you have a lung, if you have a piece of bone, maybe you've got some muscle or some fat, or I don't know, brain or something, bits and pieces of conductive stuff, all with different cell circuits. You can model those different paths and do this reconstruction by sending through, basically you're sending through these currents at all these different angles. And then by doing inverse radon transform, you can then reconstruct an image.
And what's like the levels of current that's going through? Because I imagine like electrocution, obviously that's not the case here, but like what are like the relative levels of current we're talking about?
Yeah. So it's in the about 10 microamp range. So if you want to put that in perspective, say you might have heard of TDCS, which is transcranial direct current stimulation. There's also TACS, which is just the alternating current version of that. That uses milliamps, and that's barely perceptible, but somewhat perceptible. You can feel that. This is order of magnitude below that. And if you take EEG or electroencephalography, that's a very well-known technique to measure the voltages passively on the, in neuroscience. That actually measures contact impedance by sending a small current through as well, which is an order of magnitude below what I'm sending through an EIT. And the level of current that's being sent through is actually within the IEC 60601-1 guidelines for safe use on humans as well. So basically, that's kind of cool because it's a safe technique. There's no X-rays involved. The current that's being sent through is super low, so low that it's not going to interfere with any, say, electrophysiological process. So that kind of makes it like an open platform to experiment with and sort of do data science on if you want to do machine learning on the data.
Right, because you start to then put random patterns in and just see what happens, or if you already know what a certain structure is inside of the chamber, the testing area. You were saying you kind of back calculate that out with machine learning over time.
Not even with machine learning, just with a base tomographic reconstruction algorithm. You can get an image reconstruction, and then you could do machine learning over that again to get even higher definition information.
Oh, okay.
So the other thing is most of the reconstructions only use a single frequency, usually around about 50 kilohertz. You can also do multi-frequency electrical impedance tomography, where you send a whole range of different frequencies through, and that will give you the dielectric spectrum at each location in space, which gives you like a huge amount of information about what material is at any location in space. But it's so high dimensional, it's very hard to recreate an image from that. But it's all unique information. which is kind of cool because the most recent results that are coming out in papers on this technique, they apply deep learning to a reconstructed image. They do use like a reconstruction algorithm first to get a basic image, and then they improve the image using deep learning to like sharpen it up, and they can actually really increase the spatial resolution that way.
I'm looking at some of the. So you had sent me a presentation, and I hopefully we can link this, or well, at least you had done talks too. We'll obviously link to every all your talks and stuff like that. I'll probably ask you more about those too. But I'm looking at some of the reconstructions that you're talking about, and I'm trying to figure out like the 2D versus 3D type of thing. Is it like it seems like the images are 2D right now, but is it just simply a matter of passing it at regular intervals over a sample in order to get more to get a third dimension rather? Like how does this work in 2 and 3 dimensions, I guess?
Yeah. No, that's a good question. So I've only done it, and I've just been doing it in 2 dimensions, and so that's the easiest way to do it. And you can absolutely do it in 3 dimensions. You just need to have an electrode array that also covers those 3 dimensions. So one way to do that would be to have, like, say, multiple cylindrical arrays in a tank. Another way to do that, so it doesn't just have to be a tank. You can also wrap it around your body and do it that way as well. You just have to wrap it around something conductive.
Which the human body is pretty decent at, I hear.
Yeah, 80% water.
Yeah, salty too.
Yeah. Yeah, so you can absolutely do like 3D reconstructions or 2D reconstructions, and it's up to people to sort of do that themselves on the thing they want to reconstruct. But I've given 2D examples of it.
Sure.
But yeah,
that's good. I think for like visual, like you're doing the crowd supply thing too to get the tool out there, and I believe build a community around it, and that really kind of helps to bring people in, I'm sure.
Yeah. So the idea is, so this technique has only been used in labs so far, and there is an effort that's sort of hitting some hospitals in Europe because it's easier to get things out in Europe for lung imaging. And also and also monitoring breathing in premature babies. So there's and there's another interesting tool that has come out to be able to non-invasively diagnose cervical cancer. There's a company that's so all these women who have pap smears and things, and they scrape something out and then they send it away to a lab. And then, a few weeks later, you get a result, and the whole thing was kind of unpleasant. What if they could just stick this thing in? They don't need to do any sort of tissue removal or anything horrible like that. It just goes beep, and it tells you good or bad. And that company is called Zillico, and that's using spectroscopy, which is like the simple just 2 electrode version of this technique, which is sort of like, that's a great use for it. So they're just sending multiple frequencies through and getting a dielectric spectrum.
Yeah, it's really interesting too. Hearing how this is like a burgeoning, it's not. So like you said at the beginning, it's not diagnostic. You're very careful about that too because it's not regulated or anything like that, and yet it's used as a tool for potentially as researchers and stuff like that. So where is that line?
Well, I'm not making a claim. So this is a piece of open source hardware. And it makes no claim. Whereas the company Zillico, that's non-invasively detecting cervical cancer, they are making a claim to detect cervical cancer.
Yeah.
And so they have to...
That's a big claim too. Quite big. I'm sure people would be very upset if that was right or wrong in the wrong direction.
Right. So a lot, and it's good that it's tightly regulated, and they have to have a really accurate result. And they're using the simplest application of this technique to do that. And so although Spectra is doing exactly the same thing, the technique is the same, it's not saying it can diagnose cervical cancer. They've also got to, mind you, they would also have all the data from clinical trials, and they would have made an algorithm over that data to try to, up their accuracy. So they've, they created a bioimpedance spectroscopy device, great. And then they also did like a huge amount of work, and, kudos to them, gathering all that data and analyzing it. And then, putting that through the FDA or CE mark, and then actually being able to diagnose. So the technique underneath that is really accessible, and it's really powerful. And you could do other things with it too. So it's not just cervical cancer limited. And I think that's part of what I want to get out. So there's other applications in tumor detection, particularly like good at soft tissue tumor detection. And so there's like a whole lot of papers on that, like breast cancer and things like that. There's gestural control. So yeah, like people with prosthetic,
so like a severed limb or something like that.
Yeah, like people that have their limbs amputated. They get these little they get those extensions, and you want to know what the muscles in their arm are doing, so that you can try to recreate that with the robotic prosthetic limb. So this has a lot of interesting applications there as well, because it actually gets an image of how the muscles are changing in the arm. So yeah, so there's a lot of different sort of applications which are sort of interesting. And they go all scales. There's like lab on chip applications as well, which is like super tiny. So it's very scalable. The image resolution is kind of dependent on the spacing between the electrodes. So if you have really teeny tiny electrodes, you can do it in a Petri dish. But they've also done it on a much larger scale as well. And they've actually used it in oil fields to identify oil deposits, which obviously have a different dielectric constant than the surrounding soil. But to do that, they have these giant stakes, which are the electrodes that they sort of stake into the ground. And then they send relatively large currents through to do that conductivity impedance reconstruction there. So you can do it on any scale, but the resolution is dependent on the electrode spacing.
Okay. All right. That's good to know. Yeah. How did you come upon this technique, and like, why doesn't this exist in the world yet? At least maybe as a, I guess you're moving into lower cost open source kind of realm. Maybe it does exist other places, but how did you come upon all this in the first place? Maybe take us back a little bit.
Yeah. So, I've been in a few different biosensor wearable companies that are like making watches that have like heart rate and accelerometer on them. And I've actually done 2 of those startups, and they're really cool. Don't get me wrong, but I sort of, while I was sort of thinking about what information you can actually get out of those watches, like the Apple Watch now, I don't think there's not a lot of new information coming out. I don't see there being new sensors that are adding on to that. And I think the accelerometer and the PPG sensor have been sort of done quite well, and, definitely done. And we've got the information that we can get out of that. And I was wondering, is there another safe way to get bioinformation out of the body? And I actually sort of came up with a startup idea, and I pursued it for a while. And actually got into an accelerator as well and moved to China.
Oh, wow. Was it HAX or one of the other ones?
Yeah, it was HAX.
Okay.
And it was called Lear, and it's a bladder fullness device. So this was my first foray into this technique. So, in my first iteration, I actually just did it with a phone app using, at the time, my phone had an analog input port. Otherwise, no one.
Oh, headphones! I miss those things, don't you?
Right. A headphone jack, and And I generated like audio signals, and I injected them in, and um, uh, just sine waves. And I sort of noticed this sort of change. And I was going to all these different hackathons where there was a lot of doctors. What I was looking for was something that people really needed, a wearable that people really needed, so that they would keep wearing it, because I'd noticed a lot of the problems in the wearable world. Like people buy it, and then they like a week later, it's like
It's in the desk drawer.
yeah. And I was like wondering how to overcome that. And I think, you could pick people with chronic diseases and illnesses, which means, unfortunately, you have a much longer path to market. And I would just be perfectly honest here, I hadn't fully inspected, when I sort of chose this path, exactly what that path to market meant. But in the meantime, I got really fascinated that I could detect bladder changes with the simplest version of this technique, which we started with a 2-electrode version of this technique, which is just sending a current through and measuring the impedance change over time. You can just take a whiz and you notice a change, and it was like, isn't that interesting? And you just stick it on the outside of your body, so sort of between your belly button and the top of your pelvic bone.
Really? And so it just would, just because there's less liquid in there then, and it's just a different size capacitor, I guess.
Yeah, so your bladder is just, full of conductive liquid, and you just need to measure that. But there's better ways to do it. And so this technique was prone to noise. And so then we moved to 4-electrode common mode rejection technique. And then, there was still a few problems with sort of movement and things like that. But that wasn't the major problem with this concept. So people want this product. So there you go. There's a product idea. The major problem is actually the regulatory pathway on it, which is a really horrible and sad thing to say.
Because you're saying, so now maybe you could talk us through like the difference now. This would be a diagnostic device, you're saying?
Yeah, so I was hoping that it wouldn't be initially, and I actually had a conversation about it with some people at the FDA, trying to propose that it was a device to mitigate against embarrassment. It was aimed at people that had a neurogenic bladder disorder. Yeah. So that's like people who've had prostate cancer surgery. Often they accidentally cut the nerves and stuff. And, if you can't feel if your bladder's full, it's urine backs up into your kidneys and you get UTIs, and it's just, a bad scene. People who are paraplegics and things like that. So basically I sort of, they realize that it's not just a device to mitigate against embarrassment, even though it is within all of the biofeedback guidelines. It's actually a de novo application for a medical condition, because the only people that would be interested in buying it are people that have a medical condition.
And could you explain what de novo is? That a term that the FDA uses?
Yes, yeah. It means it's new. So if you've got a device that can piggyback on something else that's already been approved by the FDA, you can get it through much faster.
Oh, there was the John Oliver just did a big thing about that, because he was talking about, it was about implants. He just did one about hip replacement implants, and kind of how the stuff that piggybacks sometimes goes way too far and does really bad things, and they don't get enough approved.
I think I might have seen something like a documentary on the hip implants at some point. Yeah, and they were leaking chromium or something into the body, and they had to be removed.
Yeah, it was something bad. It was something real bad, like the metal. Yeah, I think it was the metal-based stuff. They were grinding, I think, because there's a ball in socket, and then the ball was grinding into the socket, and then it was had shavings that were going off or something like that. It gave me the willies.
Yeah. So it's sort of interesting what you where it seems very uneven, and different approaches can change this. And I sort of thought about it, and I decided that it was actually going to be a really long path to get to market. And some investors love medical devices, and many don't, because they're really painful, particularly in the United States, unfortunately, to get to market. And I had a few other things going on as well at the time that were sort of, I was like, well, now's not a good time for that. So most investors have like, what is it, 10-year funds or something. So they have to get a return on their investment. And by the time you probably like get some money, they're probably a couple of years into their fund or something. They've been scouting for a little while. So you have to go through all that in a short period of time. So I sort of thought about that. And I think I would be prepared to do that again for the right thing. But there's this other problem, is that I don't actually have a neurogenic bladder.
Like a test case that you can use, you mean?
Oh, no. I can definitely find test cases, and everybody has a bladder and urinates, which is just great. So that's great. So yeah, it sort of matters how personally.
Our market size is 7.5 billion people.
That's right. Everybody pees sometimes. Yeah. So basically, it seems that the bigger problem is actually that you can come up with these ideas, and I think some of them are good and some of them are bad, and like how it's good that somebody's filtering them. But there's all these things that you can do technologically in the field of, say, bioelectronics, where electronics and the body meet, that seem to be completely unexplored. And there's a lot of low-hanging fruit. And the question is, how do you access that or inspire people to play with it? So on the flip side, like, let's just forget about the difficulties and like think about, human evolution for a second. And, if like, I know in Silicon Valley here, people are talking about, artificial general intelligence and how machines are going to take over. And that's all well and good. But I think the only way to really compete here is for us humans to change too. We need to kind of join with machines. And I guess that's the transhuman view. And we need to do it fast. We need to get a move on. It needs this area of joining with machines. Initially, it will improve our healthcare or personalized health and longevity. But long term, hopefully, it does a lot more than that and makes us even not just healthy, but even better people than we could have ever imagined being.
Right, and I feel like whenever transhumanism comes up too, it's like that's like a scary term in my head, but I always like scale it back from like it's not cyborgs, or sorry, what's the one in Star Trek? It's not the Borg. Yeah, it's not the Borg necessarily, where you have like, you're half human, half machine. But I'm not going to say what you're thinking, but when I think about it, it's more like it's monitoring internally. It's having like insulin pumps when you need them. It's stuff like that, where there's interfaces to the body, but not necessarily like replacing all of the body. Is that how you view it?
Yeah. So I think we can. Partly, I think that's where it will start. We should have. There's an open source insulin pump project too. That's pretty cool and has taken a really interesting approach. I should. I forget their name right now, but I should link you to them later. I've spoken with them. Yeah, the way that they got around it, because their thing kind of is diagnostic, is that they've just put the plans online.
Yeah.
And you've got to make one yourself. And so you take all the risk on, but then your blood sugar, and if you're diabetic, that's obviously, a life or death situation.
Right. Yeah. It's going to
depend.
Yeah.
Yeah. It's very, very serious risk you're taking.
Right, and it sounds like in the same manner too. You're kind of saying like, okay, say you are going to take these risks, you don't even have the way to peer into the body, and that's kind of like the tools and the things that you're working on here with Spectra. You're giving more insight into the body, just like a sensor might.
Yeah. I mean, it is a sensor, and by looking into the body, you can determine all sorts of things. Like a low-hanging fruit for this one might be pulmonary edema or water on the lungs. And there's some initial really great research on that already, basically showing that you can do it. And so there's a problem. How about looking for mucus nodules on the lungs? That happens to be tuberculosis and cystic fibrosis. Cool. There's another two things. What about so, quite a few people bought them for sort of interesting applications. Somebody's looking at trying to detect cavities in teeth with it.
Oh wow, nice.
Yeah. So there's all these sort of different things. So if you imagine sort of imaging costing a few $1 million, and it's a general tool, an MRI or a CAT scan, it can be applied to all sorts of different things. Bone breaks, wonderful. Or not wonderful, but it's great that we can see where they
right.
are.
Good to know, right?
Yeah,
right.
Yeah, and then we can see how bad it is, and then we know what to do. Awareness is the first step to doing the right, like making a good action.
Right. If you can't measure it, it doesn't exist, kind of thing.
Right.
But in this case, you might feel it, but it doesn't exist. that bone is not broken; it just doesn't exist.
Right. Exactly. So yeah. So if we can create but the problem here is that it's actually hard to get this information out. It's not readily available. As I mentioned before, 2/3 of the world doesn't have any access at all to medical imaging. An example of where we should be using MRIs all the time but don't in the United States is in breast cancer imaging, which I think happens to women over a certain age every year. They sort of do this do you have any tumors in your breast or something test, and the best way to do that is with an MRI, but we don't do it with an MRI because the costs are too high. And the weird thing is, why is an MRI still so expensive? It's been around for a really long time, right? And it's not coming down in price because it doesn't need to.
I always assumed it's because there's huge magnets in there too. I figured that
it's got huge magnets.
But like you're saying, I guess there's not a lot of new players in the market, right? Because they can't get the same dollars that a GE Medical could, or whoever else, Philips or whoever makes them these days.
Yeah, I think that's part of it, and I think a lot of people just see it as not an area to innovate in. So there's a whole bunch of people that are into ham radio, and that's super awesome. Yeah, and there's I don't know, a Lime SDR, and there's all these people that are into software-defined radio, and that's a whole movement, and all these people are excited about it, and so it's moving forward. But I think we could do that with biomedical imaging, and we could do it safely. And as long as you're doing it safely and you're not hurting anyone. And we're not going to talk about diagnosis too much. We're just going to look inside, and we can notice muscle movements or sort of nerve, peripheral nerve activity and things like that. That seems like a no harm done.
Yeah, I think my brain at first is well, no, I can't look at my, I can't do that. That's what doctors do, or that's, and I think that's it's kind of baked into my brain at least as well. I'm just speaking personally.
Yeah.
But if you, like you're saying, if you start to make this tool and you make it more accessible, then people get more comfortable doing these things. And yeah, I think that could be something that opens up new innovation paths for, I guess you were talking about even gesture control, right? It might not necessarily be in a medical context, but it could be the same technology that gets used because of the things that it enables.
Exactly. So it's a general technology. It's a general imaging technology, and it can definitely be improved on, and it can enable all sorts of different things in these different directions. And just that idea, or putting that idea into people's heads that this is a hackable area, it should be like Raspberry Pis and Arduinos. I think it's just look at you can also just look inside your body. Why not? Or the other conductive thing, or that mouse over there, or your dog, or all of
Yeah,
this
if you sit
is
still for long enough, for sure. Yeah.
right. Yeah.
Well, let's talk about the actual hardware itself, because I'd love to kind of like paint a picture for people that haven't seen it yet. Obviously, we're going to link to the crowd supply campaign and the images you have online.
Mhm.
But if you could maybe paint a picture of what it looks like, and then kind of walk us through the block diagram of how it works, that'd be great.
Sure. Yeah. So basically, it has, I rely heavily on analog devices parts because they're high precision. So what it has is like a main MCU that has a dedicated analog front end that does the impedance measurement. It's got like a 16-bit A to D on it. And the way that works is that basically it's a controlled current source, and then I measure a voltage on the return side. So so basically you have this current, and then you measure a voltage on the other side of whatever the conductive object is that you're
Mm-hmm.
measuring. I like the way that I'm sort of showing it to people is in a tank, so you can reconstruct anything in a tank. You can also wrap it around things. Um, but the tank is really actually pretty awesome because what the tank gives you is a known geometry.
And so, when you say tank, what do you can you explain what the tank looks like too?
Oh yeah, it's like a little it's a small plastic transparent tank that has a ring of electrodes around the edge of it that are all evenly spaced, and then that ring connects into the main PCB, which
Uh-huh.
has
Is that
this.
so? It looks like a flex PCB coming sort of like around the edges, flex PCB, or what is that
Yeah,
material?
yeah. It's a flex PCB. So basically, the electrode cable. I thought about doing it a few different ways, and for some applications, you want like separated electrodes in the sort of way you've probably think of EEG caps and things like that. But for others, it's fine just to have it in a flex electrode array. In fact, it's kind of awesome because then you can control the spacing between the electrodes, which can help you with image reconstruction because you just need that geometry knowledge to be able to make the best possible image reconstruction. So basically, that main MCU patches out to a bunch of multiplexers, which multiplex in 32 different ways that are going out to the electrodes. Those multiplexers are connected back to the main MCU GPIOs so that you can control them and control which one's reading and writing at different times. And those multiplexers then connect to the 32 electrodes, which are in the tank.
So would you select? So okay, so and it kind of looks like this is gonna sound silly. It kind of reminds me of like the bullet time rigs. Have you ever seen those things from like the Matrix? And like like it's circular, and you're gonna be sending stuff across. You're kind of like doing, anyways. Like you're basically
I don't,
no no.
no, I haven't. I mean, I've seen the Matrix, but
Yeah,
I haven't
the
seen
way they did
rig.
it with, and it was reconstructed by the Cron folks. They do like high speed cameras too. It's basically just like it's similar to this, where it's on a ring, and there's multiple points around it, all equidistant. And so the idea being that you can, if you're turning one thing on at a time, you get like a view around this centralized thing. So I'm looking at the picture you have of the tank filled with broccoli, and so the broccoli, you would get like the electrode
Mm-hmm.
kind of like would be activated around 32 times around the broccoli, right?
Exactly. Yeah. So I've actually got these like a few articles actually. So you can see all of this stuff on openeit.github.io, and you can like see the reconstruction patterns. So you can actually like pick different reconstruction patterns as well with Spectra. So you could try using just 8 electrodes and then move to like 16 and move to 32. So the more electrodes you have, the better the spatial resolution you get. And I think it's kind of interesting to see, what the difference is between 8 and 16 electrodes. Because then you go, oh, I add more electrodes and the spatial resolution improves. And then there's different patterns, current patterns that you can send through the different electrodes. I've just picked, and this is all open on GitHub, and you can see the stim patterns in the firmware. and you select between them using like a dashboard. So there's like a dashboard that you install on your computer, and that lets you control the firmware. And you can you select different algorithms, different stim patterns, and things like that, and you can sort of see these differences in the spatial resolution of the reconstruction of the thing that you stick in the tank. Maybe it's a cup, maybe it's a broccoli, maybe it's a fish, um,
Yeah.
whatever you want. Maybe you wrap
I
it
mean,
around your wrist.
you were saying stim pattern, like stimulation patterns. Is that right?
Yeah. So basically, by stim pattern, I mean, if you've got 8 electrodes, there's a whole bunch of different ways that you can sort of you send out a signal and then you read it on the other electrodes, and there's sort of like what ordering you do that in. And 16 electrodes has a different stimulation pattern again. And you can get different results dependent on how you sort of space things out. But basically, you want as many different mixes between the electrodes as possible. So you're trying to get, if you imagine like a straight line path between electrodes, then you want as many of them as possible to be able to do a spatial reconstruction. So you'll get, typically you'll get like a higher density of those lines around the edge of the reconstruction, and fewer of them go through the middle, which means that just if it's a circle, you'll get slightly lower spatial resolution in the middle than you do at the edges.
Oh, interesting. Okay.
Yeah.
And then so when you talk about the multiplexing as well, so you're pumping current out through, let's maybe just say 1 through 32, right? So you pump it out through electrode 1. Does that mean you're using like 17 like across the way to detect then?
Yes. And also 16 and
Oh, it is.
all
Okay.
the other,
Okay, great.
all the other
Great.
ones to detect.
Okay.
Actually.
So it's not just the straight across. You basically use one to radiate, and then that kind of goes to all the ones across the opposite side, you're saying.
Yep, exactly.
So then how do you actually then sample? So like what is the sampling pattern for doing that? Because I'm imagining like an AC waveform. Is it actually AC being pumped out continuously, or is it like different levels being pumped out on different bases? So if I pump current to electrode 1, it's like pump to current to electrode 1, measure it 15, 16, 17, or all of them, and then move on and do a different level, or like what is the, is it actually like a continuous AC waveform?
Yeah.
I guess that I'm asking.
No, it's not. So it's doing so as you mentioned, what happens is that you send something out on, say, electrode 1, you read on all the other electrodes and you get your impedance measurements, and then you shift and then you send something out on electrode 2. And this is all done with the multiplexers. So they're like fast switching analog multiplexers. So they will, so for, a very, very split second, switch over and stabilize. And then you will start the impedance measurement sequence again. Yes. So so there's different ways to do EIT architectures, just to put that out there. This is just one of them. I chose this one because it was inexpensive. So the reason that, just to give you some sort of insight into other EIT systems. So I didn't invent EIT. It's been around since the 90s in labs, and it has taken like a big cart of equipment. So you get your $40,000 EEG, you get your $10,000 current source, you get, and then you sort of join them all together with an expensive switching system, and they're all these like big messes of wires on a giant cart that they like wheel around, and that just seemed so big, and it's also kind of expensive. And I was like, man, I've been doing all this like consumer wearable stuff. So my background is making things small. And I was like, I could make this smaller. Because I was reading about electrical impedance tomography, and I became really fascinated by it because it was like, wow, you can image the body,
Right.
but you need all this really expensive equipment. Wait a second, do you really? And then I sort of like looked into it. You do need to be able to make precise measurements, precise analog measurements, yes. But that's why it's got a few, and like, I mean, I actually like the most expensive parts of the bomb are the like is the main MCU, which has this like analog devices precision measurement system on it. But still, that's much cheaper than the other systems out there. So it's comparatively, basically this is a cost-effective way to do it by multiplexing the signal around.
Yeah. So I was wondering about because you had mentioned like an AC signal as well. So I'm imagining like a squirt of current going into electrode 1, and then it switches to um, to electrode 2 or whatever. But is it just a short pulse of DC current, or is there actually like a waveform that you program to go in there?
It's absolutely not DC current. This thing actually has some DC filters on it as well to absolutely make sure that that's definitely not the case.
Well, I just mean like DC turned on and off real fast is effectively AC. That's what I'm really trying to figure out too. Like,
I see what you're saying. So it's got a DDS on it, like a digital synthesis to make sine waves. So it's making these. So you're and you can actually program it to make any waveform you want as well. I might also add, so it doesn't. You don't just have to do sine waves, but I've done sine waves. Great. Sine waves work great. Well documented here. So basically it spits out these sine waves. Now it doesn't just like spit out like a single waveform either. That's not really enough. So at different frequencies, you and you might want to run this thing at different frequencies to get that different information, which is like really like kind of interesting. You obviously that takes so it has a precision crystal on it as well. So basically, you've got accurate timing. And you get back a magnitude and phase. So impedance is like, what is it? It's like the real and complex. So you've got like your resistance and your capacitive element in the phase. But I'm just using the magnitude of that return amount. And you actually need quite a few waveforms to be able to do a DFT on it. So this main MCU, what it also does is a real-time digital Fourier transform. So, So say you send out a 50 kilohertz signal or something. That's a good, why not? Then you're measuring that back on the receiver and you want to get the magnitude of that. So you do this DFT and you can get that. And you can obviously do that at different frequencies too. And it's very accurate. And that's nice because, it's good to have an accurate reading, particularly for something like this, where you're looking for these changes in impedance, and you really care about what level they're at relative to one another to be able to get any resolution at all. One of the problems with this technique, which I'll just be super open about, is when I was talking about spatial reconstruction, and this is why it's kind of limited, but it's not necessarily the end of the story, is that so current doesn't travel in straight lines. So in your tank, a lot of the assumptions are for the reconstruction algorithm that the current is going straight from A to B, like from one electrode to whatever the receive electrode is. And that just simply is not the case. Current like bends based on the inner impedances of the object. So if you've got a bone or something, if you've got like lungs which are like got air in them, the current will go around them. So it takes all these funny routes through the body, which makes it a super hard mathematical problem to solve. So people have tried to simplify it in various ways by making kind of assumptions. Like some of the algorithms are like actually like a lot of them, they assume that the body is only a network of resistors, and that's
Okay.
yeah.
Like
So you're just laughing right there immediately, but that's what they're doing, which is terrible because it isn't. It's got like
it's like a very first order approximation, right?
yes, yeah, right, yeah. It's
Wow.
so yeah. So basically, there's a lot of open room for improvement, because it's not just a bunch of resistors. It's that like every cell has a capacitive membrane as well. So that's part of it. And so that's part of the problem about how to get better spatial resolution is that there's all these limiting assumptions made.
Right.
And limiting the assumptions works, by the way. It works great.
Sure. It's a constrained problem set then, and you basically put in known things and you're like, yeah, there it is. But then you put something unknown in and you're like, oh, what is this thing?
Yeah. Exactly.
Well, I was going to ask about that too, because you had mentioned the different frequencies, or sorry, different types of cells respond to different frequencies and stuff like that. So
Yeah.
does there need to be like a library of like, well, brain tissue responds really well to 47 kilohertz, but bone responds really well to 5 kilohertz, or like, how do you actually then go about back calculating all that stuff out?
So you can just forward calculate it,
Okay.
kind of, or like, but that's a really good question. So you can obviously get a even better resolution if you already have some idea about what's in there. But there are actually, funny that you mentioned that, there are actually libraries of standard impedance data.
Oh yeah. Okay.
Yeah, for all these different bits of your body.
It's like black body radiation too. Like whenever that's not black body, but like when you're doing like radiation problems, right, you have to know the material type. But if you're just looking through a thermal camera, it's like, I don't know what I'm looking at. It's just radiating some kind of IR. And it's like, I don't have, you can assume some nominal type of material, but if you don't know what it actually is, then you don't get an accurate temperature measurement. And this kind of feels
Right.
like the same thing in that if you don't know what type of material it is, you don't know really what there's density there, some kind of stuff there, but it's not going to be as good as if you know exactly what stuff is in there.
Right, exactly. So if you know what stuff is in there, you can do much better again with the spatial reconstructions. But some of the, like, it depends what the question is you're trying to solve. Are you trying to figure out what stuff is in there, or are you trying to, like, do you already know what stuff is in there and you're just trying to determine its configuration? So
That's a good
like,
point.
which,
Right. It's not, is it a bone? It's, is the bone broken, or that kind of thing.
I mean, yeah. So that might change depending on what application you're using it for. And what you're saying now kind of reminds me of MRI. And this is like a blessing and a curse in the MRI world. So I used to work at a cognitive neuroscience lab where we had the neuroscience
cool.
imaging center at our disposal, and I've taken MRIs of every part of my body.
That's super cool.
By the way.
Yeah.
Where was I going with that? Oh yeah. They make so often when you're sort of like doing machine learning of MRI data, you use these standard models of, like, say, a brain. And I find, and this is really disturbing, because, like, my brain is not exactly the same as everybody else's brain. There's, right? Because we're not all the same person. And if you sort of try to average across all people, like, what are you left with? Because, like, the devil's
Right.
kind of in the details sometimes. And, we're
Right.
all beautiful and different and stuff. And that's part of the question.
It's like what do the Marines say is like, this is my brain. There are many like it, but this one is mine.
Yeah.
My brain is my best friend.
Yeah, it's the only one you got. So So there's this question about, like, using, like, average data over sort of individual data, and there's different routes that you can go with that. If you used average data, you can definitely bootstrap a process and maybe get better generalized results, but it's only ever going to get you to a certain success rate. It's not really going to solve the individual's problem. Say the individual has a broken bone, or, like, something that is anomalous that you want to detect in that person. So if you can sort of use a more generalized approach, to like a camera is pretty good that way. To and then
Yeah.
there's this whole area of image recognition that like is burgeoning and fast moving, and ardently hackable, which is great. So image processing really took off, or is still taking off. It's great, and you can do that same thing
Yeah. Yeah.
with the kind of sensor data that you're getting from these biomedical imaging devices. To just take an example of like Google, I think is doing this. They came out with this awesome paper. They're doing machine learning over MRI data. I don't know if you've seen some of the, and the machine, basically their results are competitive with 6 radiologists' diagnoses. So it's like one machine learning algorithm versus 6 radiologists. So it's getting there. What you can infer from this data. So I find that really exciting, except for the MRI. The MRI is really expensive and like hard to access. So if we could have a cheap, mass producible system and then do the machine learning on that, that would be even better. So people are only starting to do machine learning on EIT data.
Yeah, and it's like it's basically more data to then feed into that machine, right? I mean, that machine being the machine learning thing or the algorithms that are doing the recognition. It's like the limiting factor has been MRIs because they're so expensive, and radiologists are obviously an expensive thing as well. You got to train someone for 20 years, and they have to understand what they're looking at, whatever. So if you knock out the cost of the radiologist, sorry, Doctor So and So, it's like then you can start to have real impact, but only if you continue to put more data into the system.
Right.
Right. If you've knocked off all the cost of the radiologist, you can then really make it an affordable thing if you get better imaging and more of that imaging like you're trying to do.
Right. Yeah. So I guess, the question for me is how would you get a new imaging effort off the ground? Like, say this one, because you need data to feed into it, right, to make it useful. And then you need people to build confidence in it, and you need doctors to sort of start using it. And maybe they use it it's used sort of in a preventative way. Like, sorry to use the Theranos example, but I mean, like stick it in every Walgreens or something, and just do a yearly body scan or something. And it's just like, it's not a perfect body scan, but it's like, oh, warning, go see a doctor about this area of your body. And then the doctor says, oh, you got a warning, we'll send you to an even better imaging thing and have a really close look at that kidney of yours.
Right, exactly. It's like a triaging method of like and you wouldn't just go right to the expert radiologist right away. You'd work your way up through a GP and all the way up to the super specialist with the really expensive equipment.
Absolutely, yeah. So I don't think it actually has to compete with the top end equipment immediately. It can kind of work its way there from the sort of the low end, which is also kind of nice in that, it's always nice to help more people. So so it can be a low end imaging device that kind of grows from the bottom upwards. And as the techniques and technologies and machine learning get better, becomes more and more competitive with the top end imaging.
I wanted to ask a little bit more about the physics of how this thing's working too, because I'm a little hazy on the actual, like, if we can kind of like slow time down and think about like how the signals are moving through the system. I'm kind of curious about that. So say we're using 80 kilohertz, right? Just because you said that's the kind of the top of the range. So we're using 80 kilohertz. You pump that to electrode 1, and then the broccoli gets blasted with 80 kilohertz. And then how long is that sample on? Like, how long is electrode 1 on?
I mean, I would have to calculate that so basically you do, you also want to average over a few measurements as well to get a more precise signal. So say it takes a couple of 100 measurements and it averages over that. It does the DFT and it gets a magnitude. So you've done a little bit of averaging to get a stable result. And what that result is telling you that's going through the broccoli is basically versus something that's not going through the broccoli. tells you where the broccoli is because you've got these different geometric paths that it's taking. So basically, so you'll average over actually, what's the number? I think it's 1,032 samples.
I assumed it was like a fixed amount of stuff. Like, so if it's 80 kilohertz and it's going for 0.1 seconds, you're going to have, however many waveforms it can go into that, however many periods you get in that sample of time. Is that not correct though? Is it just like a fixed number of
in
samples?
This system? It's actually a fixed number of samples.
Okay, great.
Yes, but it only goes to a maximum of 80 kilohertz. So if you were to go to a higher frequency or a lower frequency than 100 hertz, you would need different timing parameters on that. But for this is sufficient averaging to get a stable impedance measurement over that entire range. So yeah.
Okay. So we got the 1048 or 1032, whatever you said it was. So then that goes through the broccoli. Is it like all of the other sensors is it each sensor has its own ADC as well? Or each other sensor has an ADC? Or are those then also getting multiplexed in as data points?
They're all getting multiplexed. So this is basically just an intricate dance of multiplexes going on. You send, receive, make that measurement, then multiplexer switch, send, receive, make the measurement, multiplexer switch, and wash, rinse, repeat around in your stimulation pattern.
All right, cool. So then that gets then pulled back into the ADCs. You then have this data file of however many things that happen there, and then what? Then it's like into, you said so the DFT is then internal. Is that right? Like it's already, there's an engine in silicon.
So basically that's part of why I picked this particular chip, as well as it promising these, high precision impedance measurements at 16-bit resolution. So basically you get that impedance measurement off the analog front end, and you can send different commands to the analog front end, but it's like this bit code that you write to be able to access it. And then the main MCU is a Cortex M3. So once you get it back into like M3 land, you're relatively golden. It has all the standard things that ARM Cortex M3 has. And what it does is it actually sends the data out via UART or Bluetooth. So at this point, you don't have the raw data, though you can get the raw data. But what I'm sending out is the processed impedance magnitudes. So for each arrangement of electrodes, so each send-receive pair, you get one piece of data, and basically you stream that out over UART or Bluetooth, depending on which way you want to go, that is fed into the dashboard, which is originally written in Python, but it's compiled using Electron, which is this cool thing that makes you desktop apps in a browser. So basically,
I just think it's why Slack has so much memory usage.
It's completely inefficient. Sorry.
I mean, if it works, it's fast. Who cares, right?
So if you want to do it the fast way, just download the Python. So the reason that I did that was because I was also trying to make it accessible. So there's some people say so. Not all doctors want to install like a bunch of Python libraries.
Right.
So
you're trying to make it so that people use it. I mean, that's smart.
Yeah. So basically, you can absolutely do it. Just and it's got full instructions on how to do that. Install these Python libraries. Standard ones like NumPy and Matplotlib and whatnot. Very unsurprising, but you still have to. You still have to have those libraries. Or if you don't want to do that, which some people don't, then you can install this Electron app, which means that you don't even have to have Python on your system because it's using a portable version of kind of encapsulated Python. Mm-hmm. And as you made the point, that's exactly what Slack's doing. And there's a whole bunch of other things out there, and I think this is actually a really cool way to go for like app design in general. If you want to create an app quickly, you can sort of prototype something in Python and then convert it into this browser-based app. And I sort of think, oh wow, that's like a really interesting idea. It's a pity, as you said, it's not very memory efficient, but maybe, we can improve that.
But then it's cross-platform then too, which is great for, again, accessibility. Like as a small team, I imagine that is just paramount to, like, you want to get as many people as possible. You don't want to say like, oh, you have to use, this OS with this thing and this thing, use this library. You're basically making it accessible to not just experience types, but also like OSs and everything else then.
Yeah, exactly. Just like you said, so initially, versioning is such an annoying thing to deal with.
Yeah.
Nobody likes to deal with it. And, I'm not like, actually, that's a lie. I was about to say I'm not always running all 3 operating systems at once, but actually I am through VMware. So I run OS X, and then through VMware I run Windows, and I do firmware things and EE things on my Windows VM machine, and then I also run Linux as well, again through VMware. So basically, not everybody does that, and I didn't actually do that either until like somebody was telling me that it doesn't work for them because they were using an operating system that I hadn't used it on, and I was like, oh, that's annoying. You probably have a wrong version of something. I don't know what thing you have a wrong version of, but whoops.
Right. The best case scenario for like shipping a product would be also to ship them a computer that it is destined to work with. Like vertical integration, it's really expensive, but damn if it doesn't work every time, like.
Well, yeah, but I mean, you can do that like with a Docker image or something, I think. So I mean,
maybe.
Yeah, but it's like, again, it's like, I don't know, I just don't find that super sexy for some reason. But it's a totally viable solution, and I've seen some like software packages, actually finite element packages. So so there's 3 different algorithms that come with this. One's the basic radon transform, and then the 2 others use finite element models. And for a little while, I was getting into some of these like open source finite element tools, and they're so hard to set up, and they're so version dependent. I was in this like version.
Did any of them start with GNU? Feels like anything that starts with GNU, just run away screaming. I feel like.
Yeah. And one, so basically, they like one of them had like this Docker image, and that to help get off the ground, because they knew that it just didn't work for anybody unless you had like this exact version of the operating system, and this exact driver, and this exact something, and I was like, oh wow, yeah. And so you had to have all like GCC, this one and this one and this one, and so yeah, it's really nice to sort of think of ways to escape that, because I, for one, would prefer not to spend my life in version hell, but I think
or even writing software at a certain point. I mean, like, you do hardware, you do software, you do it all. And if you're just doing versioning stuff, it's like, oh boy, you're just in software land for the rest of your life.
Yeah, and you're not even in like I don't find that very interesting, software land either. I would rather be doing something new or not just dealing with versioning issues. So yeah, I find that. I mean, unfortunately, to be honest, I've spent quite a lot of time dealing with versioning issues, but it's not my favorite thing at all. Yeah. So, and that was a problem with this project too. It didn't start out in this Electron format. I actually started talking with somebody called Marion, and she actually made this piece of software called Cloud Brain, which used Electron. And she's actually a contributor on the OpenEIT project as well.
Oh, great.
And she was like, basically telling me about, version, like if you want to get around it, you could do it this way. And I was like, oh, that's great. That's so exciting. So basically that's how it sort of switched from its original. It was using Matplotlib and things like that.
Yep.
Right. What else was it using? It was like using Qt or something, a Qt backend. And then it moved into this server-based model, which is kind of just runs on a browser, which is sort of more generalized. And it's like, that's actually not a bad option if people have different operating systems. But there's still some limitations with different operating systems that are actually quite hard to get around.
Mm-hmm.
So, like, for instance, the Bluetooth.
Yeah, I was going to ask, what is the Bluetooth being used for?
To get the UART data off. So the thinking was that so basically, if you want a really sensitive measurement, you probably don't want a power source plugged in, and or it connected to a computer. And a really low noise power source is actually so you can obviously get these very expensive power sources, which they use in these big carts of equipment, EIT systems. But another really low noise power source is a lithium ion battery.
That's right. Yeah. Yep.
So a lithium ion battery, yay! They're all over the place. Great, let's stick one of those on there. That means you can't connect to anything else.
Right.
So Bluetooth. So if you want to get a really clean signal, use the battery.
And then so it just goes as a serial port then on the computer side as well. It's not like going to a mobile app or anything like that.
No, it just goes to the computer. No mobile app, because that's a little bit overly. I mean, this is an open source hardware software project. It's not really a mass consumer product here.
Right, but that also means that someone could go and make an app for it, and just because that's what open projects are great for, right?
That would be awesome. Most welcome to do that.
That's really great. So you are making these right now. I mean, so we didn't get a chance to connect when the project was going on, but you were funded $37,916 raised on crowd supply. Congrats for that.
Thanks.
How's the manufacturing going?
Good. So basically, I've been making a test jig, using a Raspberry Pi and OpenOCD, to flash things, and that's all working. I've ordered, so it has some custom cables, and I've sort of organized for them to be made. I've ordered the Flex PCBs, which are the ring of electrodes. And I'm currently hunting down a couple of pieces on the BOM to be able to get the main manufacturing run started. So that's basically where it's at right now. And then hopefully we can get that running and then make them all. But yeah, all the parts are ordered except for obviously the main PCB is the key part.
Yeah, the expensive part, huh?
Yeah.
And you had mentioned too, so if any ADI people are out there and you want to support a good project, this is one to throw some weight behind. This is those do not. I was just looking at the parts on the crowd supply page too. The ADUC M350 we've actually mentioned on the show before, because I remember when that came out. It came out like 4 or 5 years ago, I think. But I just remember like seeing that. Yeah, the analog front end stuff was just like. It's really, really good low noise stuff, and then it's got the micro in there too, so it's great. I mean,
yeah, it's a really nice MCU. It's low power. It's like precision, and it's made for impedance measurements, which is perfect.
Yeah.
And it's also using analog devices, multiplexers as well. The ADG
I guess
7
four of those is not cheap then, huh? What was the part number? Sorry.
ADG 732. So would love and differential amplifier as well from analog devices. So it's using it's sort of quite a few analog devices parts, and those are the major major costs on the BOM there. Such as life, but that being said,
they keep all the fancy stuff in silicon these days. That's the problem.
Yeah, and I can see why. I mean, it's sort of it does mean that you want to buy the MCUs, but if you look at like comparisons, so a comparative current source would be like there's something called the Keithley 6221. That would be the current source that I would recommend for people that wanted to go even deeper. And I think that one costs about $7,000 just for a current source. So
I
then you
actually I used to work on that. I used to work on the supporting that piece of machinery at Keithley, and uh,
really.
I broke a couple of them, and it was not good.
Oh,
Yeah,
oh,
but yeah.
yeah. That one is commonly used, sort of in this area. It seems. So yeah. So if you're not sort of using that one, then the ADU CM350 is a good option. But it's yeah. Everything has its pros and cons. So yeah, yeah. So basically, yeah, ARM Cortex M3 is nice as it's pretty standardized going on there.
Hmm.
There's nothing surprising.
How is it programming those parts? I always imagined that the ADI programming environment wouldn't have been that friendly, but maybe it's not bad.
Um, you know, pros and cons. They had some reasonable examples. Some things were a little bit obscure, but it wasn't too bad to sort of make sort of custom analog front end um, sort of it's bits of code as well. So yeah, I
Hmm.
mean it was fine,
It's like a good
but
starting point and being able to build off that kind of thing.
yeah. So they have a whole bunch of examples which are pretty good starting points, and you can kind of I recommend starting with the starting points. Always a good place to start.
Do you so how much do you how do you reconfigure like the multiplexing happens external to the parts? So I'm guessing you control that logic that actually turns on the different paths and stuff like that.
Yeah.
But then internal to the ADU CM350, does that have a lot of like configuration of the muxing between different input lines as well, or is it more like you plug in inputs 1 through 32 and it just does its own thing then?
So I mean, I'm control like so. There's custom code to control all the multiplexes. So it doesn't. It's not
Hmm.
made to.
Yeah.
So the ADU CN350 is not made to be an EIT system.
Okay. Yeah. Yeah.
So it's not made to like do that, but you can also make it do that. Um, and what it's actually made for is these precision impedance measurements, which is pretty good. Um, and so there's a lot you can just do with just impedance measurement by itself, which I could also get into as another like topic. And there's a mode in firmware that you can go into and just look at the time series impedance data, which is super interesting. You can
Oh,
see
that's
breathing and
awesome. Yeah.
heart rate. And that's actually like it's different from an ECG signal. So you can sort of see these material changes through any object, which is actually pretty awesome. So yeah, so basically then once you send the command to the analog front end on the ADU CM350, it just runs that entire command until it exits. So there's
Oh, that's
yeah, so there's
great.
not a lot
Okay.
of back and forth there. Well, I mean there's, in and out.
Right. It's not like low level control. You're saying
No.
it's just kind of a subroutine that the part's set up to
That's
do.
right. That you that
That's
that you
awesome.
execute, and you can change that subroutine. And as I mentioned, you can generate any waveform you want with it, but I'm just generating sine waves. So you can so all of that is configurable, and you can see the examples of that. And once you send that, it just runs until it finishes, um, and and then you could multiplex and run it again, or you or do whatever you want.
Yeah. Yeah.
Yeah.
Yeah. That's great. That's great.
So basically, so it's a health meter on a chip is actually how that part is advertised as well, which is sort of interesting in a lot of
Okay.
ways. That
Yeah.
it's sort of they know exactly what kind of applications that they're going for, which isn't that surprising. But yeah, that's great that they've figured that out.
Yeah. I'm looking at the data sheet right now. It says point of care diagnostics, body worn devices for monitoring vital signs, and then well, I don't know these words. Amperometric, voltometric, and impedometric measurements. So that's probably that's the kind of same
Yeah,
thing you're talking
yeah,
about here,
yeah.
right?
Yeah, and as I mentioned before, so in so far I'm just using the magnitude of the impedance signal, but there's also a phase. The phase actually has lots of information in it too that could be used. I just haven't been bothered personally. Yeah, but it's
Sure.
there.
Well, and that's like something as you build your community out too. Like I imagine like there's the pulling in the phase information. Like you said, you're using sine waves right now. I'm sure that there's something if, you start doing different waveform excitation waveforms, you could probably do other things in the future, but you're building like a scaffolding for all this stuff to happen, which is great. How has the community response been so far?
I mean, it's good. It's sort of tricky as well. There's a bunch of people who bought them for sort of interesting different applications. A lot of them definitely sort of commercial in nature. And there's about like 7 people that have sort of contributed to like the OpenEIT GitHub repository. So those are people that have sort of contributed to the project. So basically there's contributors, and then I mean, the major problem has been that not everybody has one yet. Because
yeah, right. Hardware problems are still the thing. Atoms are not easy to get a hold of sometimes.
Yeah. So there's about 7 people contributing. There's a Discord channel as well for chatting. But not everybody has one yet because I only just finished the crowdfunding campaign. So once everybody gets one that has been interested and starts using it, I think that will be really interesting to see how they start interacting and what they start doing. So I try to sort of like suggest like you can put issues on the GitHub repository and things like that, but I try to suggest different directions that people can take it in as well. So a lot of people bought it for specific applications, like I mentioned, the cavity detection, and somebody else is doing the prosthetic limb control, and so basically there's like people that have specific things in mind for it, but there's also somebody got it because they're really interested in inverse problems, and they and that's their passion, is to try to get better results on these types of inverse problems, and this is a really classic inverse problem. So it'll be super interesting to see what happens when people actually get a hold of it. So there's about There's about 6 out in the wild right now that sort of happened before the crowdfunding campaign, and so there's this new batch now that will be basically the crowd supply campaign was a kind of launch of the project.
That's great. Where can people find out more information about the project? So first off, can they still back the project, or is it kind of cut off now?
You can still back it. Just taking pre-orders now. So basically, if you go to like crowd supply and look up Spectra, you should be able to find it, and you can get one. And if you want to see everything, there's like tutorials online at openeit.github.io. And so you can see all of that there. And so basically that tells you how to install it. Tells you about the sort of different modes and firmware that you can try out to get off the ground really quickly.
And where can people follow you online if they're interested in learning more about the stuff you're working on?
Like, you mean my Twitter?
Yep, that's usually what I'm asking. And as
Oh yeah, I'm Rintoul on Twitter.
All right, well, Gene, thank you so much for telling us about this stuff. I think that this is just, it's great that it's like a new type of technology out there, and it's accessible and it's open, and I'm really glad that you're doing this stuff and you came to talk about it. Like it's a great, I think it's very electronicsy introduction into the world of medical. It's like, it feels like a really good merging of the two. And I appreciate you doing this stuff.
Thanks. Yeah, I'm obviously really into this kind of melding of electronics and humans. So yeah, it'll be interesting to see where it goes.
Yeah. All right. Well, we'll talk to you soon.
Great. Okay. Thank you.